Hello friends, today we will start differential amplifier. Now before going to differential amplifier, uh, I would like to tell you two things. We have seen two amplifier, one is common source, other one is source follower amplifier or topologies. So in this common source topology, we have seen we able to get high gain, but but biasing is difficult. In this topology, biasing is easy, but gain approximately unity. So we will review why so. So this is our common source, this is our source follower, this is common source, this is source follower. So why gain is higher here? Gain is high because here output is very high, output resistance R out is RO. Here R out equals to 1 by GM, and GM equals to GM of circuit, transconductance of circuit is GM. Here you need to find out GM. How you will find out here GM? So here you need to short and you find out ISC. ISC equals to what will be ISC? So this is GM VI. So here GM is GM. So GM equals to GM. So here gain is 1. Here gain is GM RO. So here GM is minus GM. So gain is. So now can we add these two? Can we add these two to get benefit of both? Yes. So how we will make this? Say this is common source amplifier, and okay, 1 minute. So I will draw in some other way. So you can draw it like this as well. This is common source. You take say some RL. So this is your common source. This is your common source. Here you will have some bias current, say IB. So say this is IB, and you connect here. So now in this case, in this case this is your common source, this is your common source, and this is your source follower stage. So basically we are combining both to get differential amplifier. Now I will draw this again. So in this source follower, this V tail, say VT, V tail, or okay, okay, yeah, V tail is decided by input bias or input quiescent point. This will be you will V tail, say Q is quiescent point, so equals to V in Q minus VGS. Okay, so in this arrangement biasing is easy, and this IB current bias your V out Q, V out Q equals to VDD minus IB into RL, because in symmetric condition IB will flow here and IB will flow here. Okay, so these are the biasing conditions. So I will draw this again and we will see how to find out differential amplifier gain, DC gain. Okay, now this is VDD, this is RL, this is RL, this is V in Q, this is V in Q, and this is IB, this is IB, this is unless, this is W by L for both. Now suppose we give here delta V, we give here minus delta V. So basically we are giving differential input to our differential amplifier. Now this tail node V tail Q will be, so this will act like a, this portion will act like a source follower, this. So if we are giving some AC signal or we increase this by delta V, we reduce this by delta V. Now if we are increasing this by delta V, this node will go up by delta V, and if we are reducing this by delta V, this node will go down by delta V. So plus delta V minus delta V. So this tail node will remain at its quiescent point. It is not going to change. So it means this tail point is on AC ground, or you can say virtual ground. So what is AC ground? Basically this is small signal ground. With respect to AC signal, if some node is not changing, that node is known to be a AC ground or small signal ground. So say in our bias circuit, if I am taking some bias current here, this is constant or DC. So when we do small signal analysis, we usually make it ground. In actual it is not ground, but for small signal this is known to be ground, because this is connected to some constant voltage, constant DC voltage. So this circuit is ground. So now for a differential case, circuit reduced to this circuit. So now this is V in